Okay, so welcome back. In the last video, we talked about partial dependence plots, ICE, individual conditional expectation plots, and accumulated local effects. In this video, we'll pick back up, starting with feature interaction plots. So suppose we want to make a prediction based on two features, say x1 and x2. We can split or decompose our prediction into four terms. It's a function of x1 plus x2 plus some interaction x1 times x2. Now here we're not focusing on predicting with this as the functional form of the machine learning model. Instead, we're trying to explain the prediction that resulted using this functional form. So that H statistic is something that we can use to measure how much of the variation in the prediction depends on the interaction of the features. So how much of it depends on this product, x1 times x2. This interaction measures the dependence between the features, so how x1 and x2 are themselves related. So the formula for the H statistic is provided. Some things to notice here. This H statistic is a function of the partial dependence between the variables. So essentially, we're summing the partial dependence divided by the partial dependence squared. So we're calculating some measure based on this dependence. If there is no relationship or no interaction between the features, this H statistic will be near 0. If this H statistic is near 1, then all of the variation of the interaction term is explained by these partial dependence functions. Now, if this is greater than 1, then the variance of the two-way interaction is larger than the variance of the two-dimensional partial dependence. So we can create these feature interaction plots using this interaction new option. Essentially, what we're looking at here are features that have a strong interaction and features that have a small interaction. So for example, there is a big interaction or a big or strong relationship, relatively speaking, between the cleanliness of the flight, so how clean the customer is perceiving the aircraft to be, and the class. So you might expect that flights in business class or first class tend to have cleaner seats or cleaner areas. There is some relationship, but less of a relationship between legroom in class, seat in class. There appears to be a relationship between customer age and class as well, experience with baggage and class. This interdependence or interaction between ID and class, I would wager that some customers are flying business class very frequently. Some customers are flying economy very frequently. As you can see, these interactions between class are sorted in descending order. All of these features are computed or calculated in relationship to their interaction with class. So we're looking at interactions with one variable at a time. If we tried to look at interactions with all variables at one time, this plot would become very large and unwieldy. So some advantages of this. There's a very meaningful interpretation of this. How much variance in the data is explained by this interaction. This is a dimensionless measure, which is also very nice to look at. Large H statistics are on the same scale, no matter what. And this works for all kinds of interactions, regardless of variable form. So categorical versus numerical doesn't really matter. Disadvantages here, they're computationally expensive, so this does take a little while to generate such a plot. And then finally, there's no measure of significance. So is this a large H statistic? Certainly, relatively speaking to the rest of them, yes. Overall, there's no real understanding or measure of the distribution of this thing. Next, let's talk about global surrogate models. So the idea here is that we want to take the underlying complex machine learning model and try to approximate it as closely as we can with a model that has intrinsic interpretation, so a model that is much simpler. The way this works is that we start by fitting our black box model. So here, black box just refers to a model that is difficult to interpret. We'll fit that model and make predictions. We'll then choose an intrinsically interpretable model, such as regression, and fit it to those black box predictions. The idea here isn't to produce a surrogate model that matches the output variables, but rather one that predicts or replicates the predictions from our model. Because if we can replicate those predictions with a simpler model, then we can understand how those predictions may be constructed. So we can try to interpret our decision tree, for example, by building a single tree as a surrogate to our random forest. This tree is explaining about 57% of the original variability in the random forest. The big factors that we're seeing here, if we're looking at business class and boarding online not being very satisfied with it, then that predicted satisfaction tends to be pretty low. However, if we have a business class customer who is fairly satisfied with their online boarding experience, then they tend to be pretty satisfied with their flight as a whole. Looking at economy and economy plus, in-flight Wi-Fi seems to be the kicker to getting someone to be satisfied with their flight experience. Here we've limited this tree to only a depth of 2. We could also apply a surrogate model such as logistic regression. So here I've fit a generalized linear model using a binomial distribution or logistic regression. The correlation with this compared to our more complex model is pretty high. We're explaining about 81% of the predictions. Here we can look at this output and see which variables are important based on the p-values and how those estimates are being affected. Now, global surrogates have a disadvantage in that they're trying to predict the model everywhere, so they may not be as fine-tuned. We can use a local surrogate or a LIME model, standing for Local Interpretable Model Agnostic Explanations, to train surrogates in a small area. So rather than trying to predict over the entire region, we may try to predict a small region of satisfaction. So essentially what we're doing here is looking at what's happening to the predictions when we give variations of our data into the machine learning model. So we'll generate a new data set to do this that consists of permuted or shuffled samples and the corresponding predictions of the black box model. So we'll slightly tweak our input variables. We'll train an interpretable model on the new data set and see if we have a good local approximation. The details here are what is the most challenging. So here's the basic algorithm for this LIME model. The open questions or the judgment calls that the practitioners have to make. How are we going to perturb our data set? How much are we going to change the input variables? How are we going to weight the new samples according to proximity? And then how will we explain the prediction? So there are actually several implementations of this LIME method in both R and Python. There are some differences in how they think. So if you apply this in one language versus another, you will see some slight differences in these LIME outputs. What gets produced then is an effect. So we're looking at how much each of these feature effects affects the local prediction. So for observation 1, just looking at the first row of the prediction, our actual prediction using the complex machine learning model is a satisfaction probability of 0. So we're predicting that this individual will not be satisfied with their flight experience. The local model's prediction is 0.33. The local model is showing a positive effect, so an increase of boarding online. So we think that for customer 1, this boarding online experience will really be helpful. Customer 1 is an economy class, so that's bringing the prediction down. Customer 1 is traveling for personal reasons, that's bringing our prediction down as well. Looking at a second customer, this is observation 415, our actual machine learning model, so our black box model predicted satisfaction probability of about 0.08. The local model predicted a much higher satisfaction for them, so missed pretty dramatically. Features that contributed to this local model prediction in a big way are the boarding online. This customer was very happy with their online boarding. This customer was also traveling for business. The advantages of these surrogate model techniques is that we can use a black box model for prediction. So we can use a very complex model to predict and then try to understand it with a very simple model. This works for text data as well as image data, so we could apply something like the MNIST data set to try to get an idea of what pixels perhaps are very important or what features of, say, an image are important for prediction. Defining this neighborhood, so how close or how much we want to tweak the observations, that is an open problem. Then explanations of two similar points can very greatly depend on random sampling. So if we are randomly shuffling these points, there's a lot of variance in the surrogate model and Lime explanations. The last class of model agnostic interpretability measures that I want to talk about are Shapley values, or based on Shapley values, I should say. So what are these things? Shapley values are taken from a field of mathematics called game theory. So the idea here is that we're assuming that each feature value is playing a game. The prediction is the payout. How do we fairly distribute that payout among the input features? So the Shapley value of the J feature is how much it contributes to the prediction for a particular instance compared to the average prediction. So this tells us how much more important feature J is to that observation compared to the overall average. Positive Shapley values indicate that a feature is more important for that observation. Negative would indicate that it's less important. So let's look at instance 1, or observation 1 again. We have our average prediction 0.00. The average prediction, so this is the average prediction over multiple resamples. So notice that we've got some variability here. The things that are most important, we think, to this first observation, they were pretty happy with their baggage. They were happy with their in-flight services. They were a loyal customer. The entertainment and food and drink, they were somewhat happy with. These were all pretty important to them. These were important features for this customer compared to the average. Things that were not as important or had a negative Shapley value. Economy class wasn't as important. Boarding online, medium experience wasn't as important, or rather contributed in a negative way for this customer. For customer 415, business travel contributed in a positive way. Being a loyal customer contributed in a positive way. Boarding online, they were satisfied with it. Things that contributed negatively to their flight experience, check-in service, and flight Wi-Fi was only a 3, baggage, and it looks like there was a delay for this customer. So some advantages with these Shapley values. There is a pretty long history in the game theory literature of Shapley values, whereas some of these other model interpretation measures are much newer, so they don't have as much theory behind them. We can compare our predictions with these to average predictions. We can compare to subsets or other data points as well. There is a disadvantage here that comes from interpretation. Specifically, these are not the difference of the predicted value or the contribution of a feature to the difference between the actual and mean prediction. So they're not interpreting that specifically. It's a measure of importance more than anything else. That means that these explanations are not simple. So the last interpretability measure that I want to talk about are SHAP, Shapley additive explanations. So these SHAP values create a global interpretation. So we're looking at how this is being created or how the Shapley values are contributing over a set of M observations, a set of M instances. We can look at a set of customers that are similar, or we could look at this over the entire data set. These are similar in some ways to those Lyme predictions, but they are a little different. Lyme weights according to how close these disturbed instances are to the original data point, whereas SHAP weights according to the weight from the Shapley value estimation. So they're similar. All right, so in summary, we've talked about how you can look at various components of a machine learning method. You can look at how a feature affects the predictions using partial dependence plots, individual conditional expectation plots, ALE plots, and SHAP values. You can look at relationships between or interactions between features using feature interaction plots. You can also use what's called a variable interaction network, which we've skipped in this set of slides. You can look at partial dependence here as well. If you want models that are approximations, you can use a global surrogate or a Lyme technique. If you want to look at individual instances, how those are affected, you can use Shapley values or Lyme. This last slide here, I've provided a set of software options that you can use in both R and Python. Now, unfortunately, Python is a little bit behind the curve as far as interpretable machine learning methods. Part of that has to do with differences between the target audience for the two languages and the developers. Python being primarily used by computer scientists who tend to be less concerned with interpretability and variability of predictions than, say, statisticians. So that's why you see a lot more options on the R side than on the Python side. So for your last homework assignment in this class, I've produced a set of interpretability plots. Your task will be to not reproduce those plots, but simply to take those plots and make predictions based on them. Your final homework assignment is bonus points, so it's completely optional for you to take on, but if you choose to do so, you can earn some extra points toward that final exam next week. Have a great day, and I'll talk to you guys later.